Bismillahirrahmanirrahim. Dear students, we start our lecture after the midterm. We start with the topic chapter number 415, power series and Taylor series. You are already familiar with the term series. Here we discuss series for complex numbers and Taylor series for complex number. Okay, we start with the term sequence. Sequence. You are familiar with the examples like 1, 2, 3, that is arithmetics progression, 2, 4, 8, 16, that is geometric progression, 1, 1 by 2, 1 by 3, 1 by 4, and so on, that is harmonic progressions. This arithmetic progression can also be written as f of 1 is equal to 1, f of 2 is equal to 2, f of 3 is equal to 3, and f of 4, and so on, f of n is equal to n. Similarly, geometric progression, f of 1 is equal to 2 power 1, f of 2 is equal to 2 power 2, f of 3 is equal to 2 power 3, and so on. F n can be written as 2 power n. Similarly, harmonic progression, that can also be written as x1 is equal to f of 1 is equal to 1 over 1, f of 2 is equal to 1 over 2, f of 3 is equal to 1 over 3, and f of n is equal to 1 over n. So that means every sequence can be written as in function form. So we can say that a sequence is a function whose domain is set of integers and natural numbers, or sometimes set of positive integers. If range of the function is a real number, then we say that the sequence is a real sequence. If range is a complex number, then we say that this one is a complex sequence. Generally denoted xn is equal to brackets for real numbers, and zn is equal to zn for complex sequence. We say that sequence convergence of the sequence converges. For this we consider the example. Let it be 1, 1 by 2, 1 by 3, 1 by 4. This one is a harmonic sequence. We draw it on a line like real line. Let it be 1, 1 by 2, 1 by 3, 1 by 4, so on. We noted that this sequence goes to a number, we call it here to be 0. So we say that this sequence converges to 0. That means note that 1 is the x1, 1 by 2 is 1 by 2, x2 is 1 by 2, x3 is 1 by 3, here x4 is 1 by 4. After 4 term, this distance between every 2 points of the sequence is less than 1 by 4. We say that this sequence converges to a number that is called 0 here. Then after certain number of points, sequence terms close to each other, we say the sequence converges. Okay, that's the proper definition. The power series of sequence. A sequence is a function whose domain is a set of positive integer. In other words, to each integer we assign a complex number, let it be zn. Convergence of a sequence, limit and then to infinity zn is equal to n. We say that the sequence converges to that number, convergent and converges to number n. Series, some of the terms of a sequence is called series. Next is the convergence of a series. What it means, we consider here the sequence of infinite terms. Let it be an infinite series of a complex number is to be z1, z2, z3, so on. We say this series converges, that means sum of this series is to be a finite number. What it means, how can we say that the sequence converges, series converges here? That's convergence of a series. And how can we find sequence a series converges? आप किस तरह डिस्कस कर सकते हैं कि हमारी सीरीज कन्वर्ज कर रही है? तो उसके लिए हम डिफाइन करते हैं पार्शियल सम्स Sn is equal to Z1, Z2, Z3, Z4 and plus Zn, n term sum. S1 is 1 term, S2 is 2 term sum, S3 is 3 term sum, S4 is 4 term sums, and so on. Sn is n term sums. We said if this partial sum sequence, we define partial sum sequence, if this converges, then we say that this series converges. What it mean? If this partial sum converges to some number as n tends to infinity, then we say that the series converges to that number that is equal to L. Now how can we find our series to be convergent or divergent? Divergent if the sum is not finite numbers. As n tends to infinity, this power sequence, partial sum sequence not converges to a number. Okay, for this we have different tests from which we can say that our series converges or not. Okay, let it be supposed that we have there is a test, different test we discuss here, the ratio test. Suppose Zn is a series of non-zero complex numbers. That means 0 is not the member of that series. For this we define a ratio Zn plus 1 over Zn, nth term and n plus first term's ratio, and limit n tends to infinity if this ratio tends to some number L. Okay, if this L is less than 1, then series converge absolutely. If L is greater than 1 then, or infinity, then we say that the series diverges. If this L is equal to 1, this test is inconclusive. That means a ratio limit is to be 1, then we cannot say anything about that, okay, whether series converges or diverges. This is the ratio test by which we can check that whether our series is convergent or divergent. Okay, now consider general power series. An infinite series of the form, let it be a n z minus n naught power n, if n varies from 0 to infinity, that n is equal to, for n is equal to 0, that is n a naught, n is equal to 1, a1 z minus n naught power 1, a2 z minus n naught power 2, a3 z minus n naught power 3, and so on. With the coefficient an are complex numbers, is called a power series in the power of z minus z naught. The series is said to have center z naught, and complex number that z naught is referred to as a center of the series. We call z naught as a center of the series. For example, here this one is a series, a power series. Here's center is minus 2 iota, and here coefficient is n power n over n factorial. An is to be this one. We say that this power series converges. What it means? That means this infinite series sum is to be a finite number. Here we have series in term of variable z. We say that for what value of z the series converges. Series give you finite value, but here series is to be infinite. Okay, for z values here are different complex number for which this power series converges. Now we find that numbers किस पैटर्न पे वो numbers होंगे. There are a lot of numbers for which this series, infinite series sum is to be finite. that is always in the region. How can we find? Here we define the term radius of convergence. What it means? That means the series converges for values of the z for which that region of number, the complex number, is to be a sometime like open disk. Of course, that open disk has a some radius. Okay, how can we check this? Okay, for this, consider this infinite power series. Every complex series has a radius of convergence. Consider this complex power series. The value of z for which the series converges to f converges may be found by D'Alembert, the scientist name, ratio test. Okay, here series converge absolutely. We must have the by ratio test. Okay, if here Zn is to be an z minus z naught power n, Zn plus 1 is an plus 1 z minus z naught power n plus 1. By ratio test is to Zn plus 1 over Zn plus 1 over Zn mod limit is to be L. If this L is less than 1, that means this limit value is less than 1, we say that the series converges absolutely by this ratio test. Okay, taking mod separately, z minus z naught, z minus z naught power n cancel. We have left an plus 1 over an and z minus z naught. Okay, taking mod separately, limit n tends to infinity, z minus z naught contain no n, so that is why we can take it out to the limit. Okay, this product is less than 1. The condition can be written as conveniently z minus z naught mod is less than r, where r is the radius of convergence and is defined to be, we call this whole expression of limit, that is 1 over r, that in other word r is limit n tends to infinity an over n plus 1. Note that here an plus 1 over an, and this one is an over an plus 1. This is called the radius of convergence. This r is called the radius of convergence. So by this formula we find the radius of convergence, that z minus z naught. This note that this one is open disk, this one is open disk with center at z naught, radius r, and this radius is defined by this, that is called the radius of convergence. Now if the series is of the form, let it be 2 power n z minus z naught power 4 n, may example other one is minus 1 power n 2 power n plus 1 over n factorial square z power 2n. The here power is to be in the form of 2n, 4n, somewhat. Then the formula for radius of convergence is as follows. Let it be, we take the general formula, general series, power series an z minus z naught power kn. If we choose a k is equal to 1, then the previous formula. If k is any other number, then we follow as per, just like we did in the previous process. Okay, the value of z for which this series convergence may be found by D'Alembert ratio test. Hence the series of converges absolutely if here Zn is an z minus z naught power kn, and Zn plus 1 is an plus 1 z minus z naught ki power k into n plus 1. Again ratio test, n plus first term over nth terms, mod limit n tends to infinity, value is to be L, and if L is less than 1, the series converges. Okay, here k power n cancel. We have left an plus 1 over an z minus z naught power k mod, taking mod separately because we know that z1 plus z1 z2 mod is equal to z1 mod z2 mod. Okay, again mod is outside the limit. Okay, now note that z minus z naught power k mod can also be written as z minus z naught mod power k. First power then mod or first mod then power k. This condition again can be written as convert conveniently z minus z naught power k mod k less than r. Here r is defined to be this one, provided this limit exists. Now radius of convergence is to be z minus z naught mod less than k power r power 1 over k, not only r. Here radius of convergence is r power 1 by k. Okay, note that this is the major difference. Now circle of convergence, every complex power series has a radius of convergence. Okay, you know that a complex power series has a circle of convergence defined that z naught is equal to r. The power series converges absolutely for all z. It's defined z minus z mod is less than r. As we define, if less than r, we see a series converges absolutely. If this mod is greater than r, that is outside the open, this series diverges. Now we consider the example how to find the radius of convergence. Okay, for this consider this example, 2n factorial over n factorial power 2 z minus 3 iota power n. Here an is to be 2n factorial over n factorial power 2 and z naught is here 3 iota. Okay, we have find radius of convergence by ratio test formula, d number formula, limit n tends to infinity an over n plus 1. Here an is to be this one and an plus 1 just replaces n by n plus 1. Okay, that is written as 2n plus 2 and n plus 1 factorial can be written as n plus 1 into n factorial. Okay, 2n plus 1 factorial can be written as 2n plus 1 2 into 2n plus 1 into 2n factorial. Just like 10 factorial can be written as 10 into 9 into 8 factorial. Here this one is that number and their previous number and their previous numbers factorial. Similar denominator n plus 1 factorial power 2 and n factorial power 2 separate. Okay, again formula using this one, an over an plus 1. Here an is this one and an plus 1 is this one. So an over and reciprocal of this one here. N plus 1 factorial n factorial square cancel, 2n factorial to n factorial cancel. We have left n plus 1 square over 2n plus 2 in 2n plus 1. This simplified this dividing numerator and denominator n square. Here that means 1 plus 1 over n whole square. Have 1 n is to be here in the first factor and divided second factor also by n. We have 2 plus 2 over n or 2 plus 1 over n. As n tends to infinity, this term 0 approaches this term equal to 0 and this term is also equal to 0. We have left 1 over 2 multiplied 2, that is 1 by 4. Here r is to be 1 by 4. The series converges z minus 3 iota mod less than 1 by 4. Hence the center is to be here 3 iota and radius is to be 1 by 4. Radius of convergence is 1 by 4. Okay, dear, you have exercise questions to solve. Find center of convergence, center of the series and radius of convergence of the power series in the exercise 15.2. Okay, next topic is to be Taylor series and Maclaurin series. We are familiar with the Taylor series and Maclaurin series for real functions. Now we have defined Taylor and Maclaurin series for complex functions, complex valued functions. General form of the power series of complex function, center as z naught is written as in this form, and 0 to infinity a n z minus z naught power n, and generally just open the series and if n is 0, n is 1 and 2 and 3 and so on. Here f of z is analytic function. Analytic function means that functions satisfy the Cauchy-Riemann equations. Okay, we just simple differentiate f dash f of z is to be a naught is constant 0, whole power 1 1, a1 left. Here derivative is 2 times of z minus z naught. This derivative is 3 times of z minus z naught. Similarly, next derivative is to be just differentiate a1 0. We have 2a2. Next term we have 6 times of a3 z minus z naught power 1. In other word, next third derivative is to be this one. Okay, this relation between the coefficients a n and the derivative of the function. Okay, evaluate these terms at z is equal to z naught. F at z naught, as replaces z is equal to z naught, all terms are finished to be 0. We have left a naught, so a naught is equal to f at z naught. Okay, next, if I replace derivative at z naught, first derivative at z naught, we have values 1 into a1. Second, in equation 3, at z naught we have 2a2. Third derivative at z naught we have 6 times of a3, that is 3 factorial a3. In general, and a derivative at z naught we have n factorial an. In other words, an is written as 1 over n factorial, and a derivative at z naught as n is greater than equal to 0. We replace a naught, an is to be here. We have f of z is equal to limit series sum is 0 to infinity, this an into z minus z naught. This one is formula for Taylor series, to find the Taylor series for complex. Similar as we did for the real valued functions. Okay, this series is called the Taylor series of function at z naught. A Taylor series with centers at z naught, this referred to be as Maclaurin series. Okay, the important special some Taylor series or Maclaurin series, generally 1 over z minus 1 minus z Taylor series is 1 at about 0, that is Maclaurin series 1 plus z plus z square, so on. E of z series is this one, cos of z series, sine of z series, cosine hyperbolic function series, and sine hyperbolic function series, and logarithmic series, and similarly binomial series. Now, how we find Taylor series of a complex number? Let it be find the Taylor series with the centers z naught and radius of and also find its radius of convergence. For the function f of z is here sine of z, and z naught is pi by 2. The given problem is to be here f of z is equal to sine z, and center is to be pi by 2. We know the Taylor series of the function is defined to be this one, and as n is 0, 1, 2 and 3 and so on. Now we find function values at z naught, first derivative, third, second, third and so on at z naught. In this case z naught is pi by 2. Here function f of z is sine of z, first derivative cos, second derivative minus sine, third derivative sine, again cos derivative is sine, cos derivative minus sine, that is minus plus. Okay, at z naught, here z naught is pi by 2, at value pi by 2, sine pi by 2 is to be 1, cos pi by 2 is 0, sine 1, all the values we computed, put these values in this series formula. Okay, we have this one series. This one is the Taylor series of function sine of z about center, here center is pi by 2. This series can be written as in summation form. Note that easily we can write, okay, first term is positive, second term is negative, third is positive and so on. We can write minus 1 power n z minus z naught power, here power is to be 2n, 2, 4, 6, that is written as 2n, and denominator is here is 0 factorial, 2 factorial, 4 factorial, that is 2n factorial. This is the general form of this series. Now we find this one is the Taylor series, required Taylor series Now we find the radius of convergence. Similarly, as we did in the example, here an is minus 1 power n over 2n factorial and center is pi by 2. Okay, by ratio test formula is to be there. Here an is this one, an plus 1, just replace n by n plus 1. Here denominator 2n plus 2, and that is also written as we did previously, 2n plus 2, 2n plus 1 and 2n factorial. Okay, again ratio test, replace the values of an and an plus 1. This one is an plus 1, this one is an. Just divide an and an plus 1, reciprocal of this. Okay, simplify. 2n factorial cancel with 2n factorial, minus 1 power n cancel minus 1 power n, and we have left only 1 power minus 1 power 1, and this, as n tends to infinity, this term is going to be infinity. So here radius of convergence is to be infinity. That means this series converges for all complex numbers, entire complex plane, for all value of z. Okay, next example, find the Maclaurin series and its radius of convergence of this function. Okay, here f of z is this Maclaurin series. There are different ways to find the Maclaurin series. One way is to be that find the derivatives. Okay, first derivative, product of these two. Second derivative, again 2 terms, that becomes to be 4 terms. Third derivative is 4 terms is converted to 8 terms, but different. We find the series by this way. Okay, we know that exponential series, e of z series is to be e of w series is to be w power n over n factorial. Now replace this w by z square, w by z square, that becomes z power 2n over n factorial. Similarly, e of minus t square series is to be, just replace here w by minus t square. So our function is here becomes here, just replace the series e raised to power minus t series. This, now integrate this series by term, that just interchange the series, summation and integration. Just like we know that f1 plus f2 integral is written as integral of f1 plus integral of f2. Similarly here interchanges, integration of just t power, only integration with respect to t, just here function of t is remains, all terms are outside the series. Just integrate this t power 2n plus 1 over 2n plus 1, just power formula, upper limit minus lower limit at t is equal to z and t is equal to 0. We have this one series. Okay, next here also a function e raised power z square, e raised power z square series is this one. Open the terms of the series and 0, 1, 2, 3 so on. We have this. As n is 1, 2, 3 on the series. Okay, use z square series. Okay, now the product of these two series, how we find the product of these two series? First 1 multiply with each term, we have this term,